Good afternoon, everyone. My name is Rob Velosnik. I'm the Senior Product Manager in the case business here at Univar Solutions. I'm one of the product managers. I focus specifically on the silicones in the case business. And I just wanted to say thank you for everyone for joining us today. We'll be covering one of our Industrial Coating Spotlight Series features today. And quick thing before we really get started, at Univar Solutions, one thing we're very serious about is safety. And we always try to start our meetings off with a safety share. So with summer, I mean, it's literally right around the corner, and this one fits in very nicely. Is why should we drink water? And one of the main reasons is we need to prevent dehydration. And during outdoor or indoor activities where you're exerting yourself, sometimes if you're just spending time outside, you're going to lose or have dehydration. You want to remember to start drinking before you're thirsty, and then continue to drink after you're done with your activity to replace those fluids. And what are some of the main health benefits of water? A couple of things that I think are really important. It helps get rid of body toxins. It fights infection. Also reduces the risk of cancer, and ultimately it improves your daily productivity. So if I could urge anyone to add something to their busy schedule every day, is start with drinking a glass of water. It helps you get your day started and your metabolism moving. One housekeeping item that we'd like to take care of, and that's during today's session, you'll be able to submit questions via the chat box feature. And the way you go about this is fairly simple. Just go ahead and click the question box as it's shown in the diagram above. You can write your question in that bottom box, and then only the presenter is going to be able to see the question. It won't be out for total audience viewing. And then these questions, you can submit them at any time during the presentation. We'll gather them during that time as they come in, and we'll respond to them at the end. And now I'd like to introduce everyone to today's presenter from the Dow Chemical Silicones Group, Jennifer Duley. And a little background, Jennifer received her bachelor's degree in chemical engineering from Michigan Technological University before joining the Heritage Dow Corning Corporation as a process engineer in the solar encapsulation business. And then after that, she later moved into the high temperature resins and intermediates product line. Currently, Jennifer is providing technical service. She drives new product development for the silicone-based performance additives, the heat-resistant resins, and hydrophobic coatings that fall into the paint, the ink, and the automotive industries. So I want to say thank you to Jennifer for being able to be with us today. And we're looking forward to having a chance to hear about one of the newest products that Dow Silicones has to offer, and that's the Waterborne silicone resin emulsion for the high temperature resistant coatings. With that, I'm going to turn it over to you, Jennifer.
Thank you, Rob. So as mentioned during today's webinar, I'm going to introduce the DOWSIL 8016 waterborne resin that was launched mid last year. And then I'll expand upon what we previously divulged with some new silicone-acrylic data and formulation guidance. I'm going to start with a short overview of sustainability initiatives that are driving waterborne coatings innovation globally. And this is going to emphasize a really important unmet market need. All of this will be before I really get into the meat of the presentation, which of course will be highlighting the delivery and performance profile of 8016, including high temperature pertinent formulation and performance guidelines. And finally, towards the end, I will explain that new silicone-acrylic study completed that further expands the breadth of possibilities when formulating with our 8016 waterborne resin. There are global initiatives that have quickly driven Dow to develop sustainable solutions, and I'll take a couple of minutes to discuss some of them. Starting with the European Union, they introduced a set of regulations which prohibits the use of organic solvents in some paints, which, as you might imagine, forces more difficult formulation choices. In addition to already banning solvents in some of these industries, as part of the European Green Deal initiative, we expect to see new regulations coming to fruition based on the zero emission ambition over the next 10 years. And second, we look at China. They have implemented similar initiatives, which all essentially aim to control the emission of VOCs. For example, the environmental protection tax was put into place back in 2018, and this just limits the VOC emissions during the production and consumption of chemicals. And then also they have a 3-year action plan that was set up in 2018, so wrapping up this year, to further fight air pollution. Beyond these nationally reaching initiatives, there are also local efforts. For instance, there's a province in China that happens to claim the biggest area for production of furniture and consumption of wood coatings, and they have banned all solvent-borne coatings. This creates quite the predicament for companies in that area. It forces them to either switch to waterborne products or move their businesses away from the area entirely. We've also seen industry-specific standards enforced. The freight container coating industry moved away from solvent-borne coatings altogether back in 2017. And we have to consider the possibility that many more may follow in the future. All of this, of course, has the potential to impact businesses on their bottom line. And as a chemical supplier, it's vital that we continue to progress with these tightening restrictions. Recognizing that global EHS regulations are driving formulators to using more sustainable solutions, we'll take a step back and consider what markets this impacts. We know that high temperature resistant coatings find utility in many industries. To list just a few that we had in mind during the development of 8016 specifically, house appliances, including gas stoves, wood stoves and furnaces, ovens, barbecue grills and chimneys. In the automotive space, we considered exhaust pipes and also the electrical and under the hood components. And then for general industrial coatings, pipes and processes operating at elevated temperatures will of course require those protective coatings to be high temperature resistant. In all of these applications, solvent-borne systems dominate today due to their superior performance. However, we do have this clear need for more environmentally friendly solutions. Consequently, the development of silicon-based waterborne high temperature resistant coatings is being more and more investigated. The challenge of this route has been and continues to be identifying or developing a formulation set to meet the demanding requirements. These performances are already mastered through solvent-based coatings, but pose a definite challenge for the water-based space. Given this need for more sustainable solutions, several suppliers have taken their stab at closing the gap in this technology. We have identified benchmark products through literature searches and also conversation with customers globally. And I'm going to refer to the products on this slide as quote unquote incumbent materials in the waterborne high temperature space, although we know that they are not truly waterborne. By looking at the safety and technical data sheets, it is known that the products still contain solvents, some even containing benzene, toluene, and xylene solvents, which of course aren't getting any friendlier. And then in addition to the literature, when formulating with the benchmark materials to gauge performance, the smell made it very clear that there was solvent inclusion. The amount of solvent included in these various products significantly impacts their flammability rating, unfortunately, which really contradicts a large reason for using waterborne resins to begin with. And when I say products include solvents, I mean all species which would be intentionally added in the product and not the byproducts of hydrolysis or condensation reactions involved in the curing mechanism. So if we run through these competitive products on the screen, we see benchmark A contains 12% solvent, some of which is xylene. Benchmark B also has a significant amount of xylene. And then the third competitive product here we benchmarked against contains toluene. While many formulators don't necessarily mind using BTX solvents in the lab, it is critical to note and begin to accept that they are being phased out in many regions globally. So for these reasons, their quote unquote waterborne benefit is really diminished, and they share a portion of that environmentally unfriendly and handleability concern as solvent-based products do today. In contrast to these benchmark products, and to address the market need for an actual waterborne high temperature resistant resin, 8016 is delivered truly solvent-free and provides very good film formation on its own, which eliminates the need for even a coalescing solvent. Now I will get into the 8016 waterborne resin. The intent or goal when developing this resin was to compete with or match performance of the traditional solvent-based silicone resins in that it would provide high temperature resistance above 500 C. And that's really just what this resin does. I could elaborate on target markets and applications for 8016, but a simple way I want you to scope out where it may have utility is by identifying high temperature needs today that are either moving away from solvent-borne paints, they're requiring lower VOC, or they're pushing for waterborne delivery altogether. Among the main features, I'll first reiterate its EHS benefits. It's very low VOC and truly waterborne without solvent inclusion. It also contains that low cyclic threshold of less than 0.1% and has a high flash point, which omits the flammability label on the SDS. The 8016 doesn't necessitate the use of added coalescent solvents in paint formulations, still securing good film aesthetics without that, and subsequent film performance, which allows for even lower VOC formulating. Beyond the clear EHS benefits, DOWSIL 8016 waterborne resin provides high temperature resistance and can be applied directly on metal with excellent adhesion. And paints we've made with the 8016 have yielded very hydrophobic films, which of course is advantageous to minimize the generation of corrosion in those heavier duty applications. Our R&D team has developed a model paint formulation, but we recognize, of course, tweaks will be necessary to achieve variations in the required performances, as the binder is only one component of a paint. And more uniquely to 8016 is its compatibility with organic co-binders such as acrylates, which can be blended in for light to medium duty applications that only require moderate temperature resistance. The formulation flexibility is going to enable formulators to dial in on specific performances. In our 2020 launch of 8016, we had initial indications of this compatibility and potential for a broader range of coating performances, but we didn't really have in-depth data to share at that time. So since that initial launch, we've dug deeper into this, and I'm going to highlight some of the data collected on these systems towards the end of this webinar. The delivery of 8016 resin is consistent with your typical emulsion. It's a milky white liquid. It is pourable, low viscosity, enabling ease of incorporation, and it is stabilized at moderately high pH. The recommended storage conditions and shelf life are also very consistent with other waterborne delivered products. When considering the delivery, the differentiation is really on the solids content. 8016 resin is delivered at 60% actives, where your typical acrylic emulsions are going to range between 45 and 55% actives. By delivering this emulsion with higher actives, we're giving formulators the option for higher solids formulations, and then also we're shipping less water in every container. This is a generic paint formulation, which was specifically designed to satisfy the performance needs for an oven cure application. As you can see, it contains most of your traditional high temperature paint components. 8016 is going to be the only resin in a lot of the data I'm going to share today, again, to address those ultra high temperature needs. The black pigment dispersion includes a blend of oxide functional pigments, which is very common and required for high temperature resistance. The functional filler we've included is silica. This is necessary for initial wet and dry adhesion, and then more importantly, post-heat adhesion. Of course, you can include other fillers. For example, you can include other reinforcing types, or you can include carbon black at low levels if needed. I've seen this included for jetness or color specifications, but it's not going to be a recommendation as carbon black doesn't really add to silicone resin function or performance. And then the additives in the formulation include 8590 additive as a defoamer, the DOWSIL 67 additive used for wetting. This further helps eliminate the need for coalescing solvents. And Acrosol ASE 60 is the rheology modifier we've developed into this formulation. It's recommended at a very low level, which again is common for water-based paints. While we are working on a formulation for room temperature cure, we recommend this formulation outlined here be cured above 180 C for an hour. So very consistent with the mature solvent-based silicone resins supplied. And finally, film thickness for all pictures I'll show was kept consistent and measured at approximately 1 mil dry. So for the rest of the presentation, I'm going to share the performance profile of 8016 through data and pictures according to this formulation range. And this is going to become the framework for recommended starting point formulations. I guess the only caveat I'll mention is that our acrylic modified formulations towards the end will have a bit of a different formulation set, but I'll be sure to call that out. Before I dive into performance, I should also mention that results presented today include paints cured in an oven for an hour unless otherwise noted. And all coatings were applied as single coats direct to metal on cold rolled steel via drawdown. So consistency maintained. Okay, so here's a quick snapshot of the performance of an 8016 base paint, comparing a 200 degrees Celsius cure to a 230 degrees Celsius cure. I'm starting to understand whether cure temperature has an impact on film performance. For both films, we measured pendulum hardness, pre and post heat adhesion according to the DIN method 2409. The degree of chalking was assessed by simply rubbing the surface of a coating after the high temperature exposure. Film cohesion was measured by the amount of dust or material peeled off during the post heat adhesion tape test. And delta E, or color change, was calculated between a cured film and then a film that had been exposed to heat. We also looked at humidity and water resistance, but I'm going to share that data on a later slide. The post-heat data for this slide and then all other data I'm going to share indicates it was exposed to 500 C on a hot plate, and this was really to simulate what the coating's going to see in a real-world application. So looking at the table summary, the visual appearance of the film was excellent regardless of the curing conditions, and the pendulum hardness in both cases was slightly over 100, which is very typical for a high temperature paint. The adhesion before and after exposure to heat, again, as measured by that loss of material, was excellent and really independent of cure temperature. We also witnessed very low discoloration. A delta E of about 2 is said to be detectable by the average human eye. And of course, this is going to vary greatly from person to person, but we're just over that detectable limit. I'm going to show you what that looks like on the next slide. But finally, the chalking resistance of the film was excellent, again, regardless of cure temperature in this case. Here's an example of what the 8016 based paint looks like before and after exposure to high temp. Both of these panels were cured at 200 C for an hour. The right panel was then exposed to that 500 C on a hot plate. Neither of the samples have visual defects or chalking, and the film integrity is excellent for both pre and post heat exposure. The sample exposed to 500 C on the right only shows slight discoloration, as mentioned on the previous slide with those numbers. It's just over that visually detectable limit. This color loss is almost inevitable. It's mostly going to be from pigment oxidation and organic substituents burning off of the silicone resin. But it's very interesting to note that we actually observed the color revert closer to its initial profile once all of these organic substituents have pyrolyzed from the resin, which makes sense as degradation and organic composition can exhibit a yellow tone. When those components have all burned off as carbon dioxide and water, they're no longer there to show any discoloration or minor degradation. The level of film cohesion was also assessed based on the amount of material removed with Scotch tape during the adhesion test. Since this adhesion test on the substrate rated 5B, or nearly perfect, we were able to visually assess the amount of cohesion by material on the tape. Had we had a less than perfect adhesion rating, we may have worried that the material on the tape was adhesion failure, but this wasn't the case. So we were able to look at cohesion this way. This performance property evaluated for 2 coating samples cured at 200 C, shown on the left, and then 230 C, shown on the right. And while 200 C is sufficient to cure the film for many performance properties that I've outlined already, the film cohesion was improved slightly when the curing temperature was increased to 230 C. And this again is just going to give us some flexibility in formulating an application depending on the desired performance. Continuing to talk about cure temperature. This is a more holistic view of the influence of cure temperature on coating hardness or film development. Aside from our theory-based recommendations and historical guidelines, This gives us a really good idea of the temperature range required to trigger that full cure in an oven by measuring hardness. On the y-axis is the pendulum hardness, and on the x-axis is the curing temperature, increasing as you move from left to right. For all of the cure temperatures in the study, the cure time was held constant at 1 hour, so consistency maintained again. Up to 130 degrees Celsius, we see relatively no curing is taking place, and the film hardness remains low. We don't see that hardness development really start trending upward until we get 130 to 160 degrees. And then, of course, we look for that point where we see a plateau, and we see that hardness plateau or the point of diminishing returns around 200 C. So this is going to be the genesis for our oven cure recommendation. Okay, looking at one more facet of cure conditions before I show other parameters that we explored to come up with our starting point formulation. Here I illustrate the impact of cure on water resistance. Panels were cured here for an hour at different temperatures ranging from 70 to 200 degrees Celsius, and then put into a humidity chamber at 40 C with 100% relative humidity. The top row shows your 24-hour exposure in that chamber, and the bottom row shows 250 hours exposure. Both rows show cure temperature increasing as you move from left to right. Critical to note is that none of these formulations had a corrosion inhibitor. We fully expect this to be part of a competitive advantage when formulating a paint, but we really wanted to understand how the 8016 performed on its own. And the results are showing that hydrophobicity is significantly impacted by curing temperature or the degree of cure. Having too low of a cure temperature seems to be detrimental to the level of water resistance within these test parameters. And then I think it's worth noting, it's not shown on this slide, but we have initial results indicating that shorter cure time at 200 C actually provides a similar performance in this humidity chamber as the coating cured at 180 C for an hour. So again, although the results here are going to give us that recommendation for bake cure above 180 C, the fact that we can simply change the cure time to tweak performance gives us extra flexibility in different applications that may have an already established max cure temp that they can achieve. Another formulation parameter we dove into was PVC. As we know, this has a direct impact on paint performance. To simplify here, I show variation in pigment to binder ratio from 1.2 to 2.8, with 1.8 as our relative chosen midpoint. And then for all formulations, we assessed color change, adhesion, chalking, and film cohesion after the high temperature exposure. The left column is showing your performance for the lowest pigment to binder ratio tested of 1.2, the middle column 1.8, and the right column is your highest pigment loading level with a pigment to binder ratio of about 2.8. All the test specimens, again, were cured for an hour at 200 C, followed by that 500 C exposure on a hot plate. The color retention does remain fairly consistent, but we did see that having too low of a PVC can significantly impact that film cohesion. And you'd say, let's increase PVC. So while the higher PVC improved the adhesion and subsequently cohesion, it appears that this high PVC formulation did tend to lead to chalking of the coating surface. So what this does is gives us a good idea of how we can tailor that pigment loading to tweak performance. Hence, while the recommended pigment to binder ratio is going to depend on the desired performance, in general, 35% binder in the dry paint, or in this case, 1.8 pigment to binder ratio, did maximize the overall coating performance, including that adhesion to cold rolled steel. To put a face with a name, so to speak, here are the pictures of formulations with varying PVC I summarized in the last slide. The formulations did not contain a corrosion inhibitor again, and were cured before being placed into the chamber at 40 C with 100% relative humidity. The left three pictures are the 24-hour exposed samples, and the right three pictures are 250-hour exposure. Each exposure time set here shows pigment to binder ratios of 1.2, 1.8, and 2.8 as you move from left to right. And the common trend between these two exposure times would be that as you move from the right to left, we see better performance or better water resistance. So in other words, as you decrease pigment to binder ratio, you improve the water or humidity resistance in this case. And this is mostly expected, confirming that the PVC of the paint can significantly impact the porosity of a coating film. Of course, this is always going to depend on other formulation parameters, but this optimized pigment loading level is represented in that starting point formulation that I shared at the beginning of the webinar. In addition to PVC and pigment to binder variations, we also looked at pigment to other functional filler ratio, or in this case, silica, as we know that this will also impact coating performance, specifically after exposure to heat. This graph depicts how pigment to silica ratio impacts the color retention of a coating after exposure to 500C, y-axis being delta E, or color change, and x-axis is that pigment to silica ratio increasing from left to right. As delta E increases, reminder, the color change is going to be more pronounced, so a lower delta E is, of course, preferred. From the chart, if you consider the obvious change in delta E and follow that trend line from right to left, silica loading increases, and this correlates to more discoloration of the coating after heat exposure. And the discoloration doesn't really stop changing until we hit a pigment to silica ratio of about 2.5, at which point that delta E is going to remain low, which is desired. Although it appears that eliminating the silica altogether would maximize heat resistance and color retention, our testing does indicate this formulation does require at least some silica for initial and post-heat wet and dry adhesion to a steel substrate. And if we want to minimize color change and maximize post-heat adhesion, of course, a pigment to silica ratio of approximately 2.5 gives us that best balance. As typical in water-based paints, adding a rheology modifier improves the stability of the paint. There are two samples shown. The left does not include a rheology modifier, and the right sample here does include that ASE 60 rheology modifier. Without the thickener shown in the container on the left, phase separation is observed, which in turn could impact your film homogeneity and aesthetics and would probably require more mixing before use. Okay, to conclude this portion of the webinar, showing performance of the 8016 waterborne resin as the sole binder in a high temperature resistant paint formulation, I want to highlight the performance benchmarking we completed. The benchmarks are going to be the same products I highlighted at the beginning of the presentation. Reminder, these are the three products that all contain some level of harsh solvent. For consistency, all coating samples here were drawn down on cold rolled steel, cured for an hour at 200C, and the formulation components and parameters were also held constant, which includes that pigment to binder and pigment to silica ratio. The only variable here is going to be that binder type or binder composition. The high temperature resistance was then assessed of the 8016 in these three benchmark products by measuring adhesion, chalking resistance, and pendulum hardness. Among all of these products, the DOWSIL 8016 did exhibit the best overall performance. If we look at hardness first, although this isn't always a definitive test to indicate performance, I know I've formulated high temp coatings with pendulum hardnesses ranging from 80 all the way to 140. There is one obvious outlier here, and that's that second benchmark product showing a significantly lower hardness. We also didn't see material loss with the tape adhesion test in the 8016 formulation, whereas all the other competitive products show some material removal, and in the sample on the right, a quite severe material loss. In addition to the excellent adhesion, no chalking was detected with the 8016. Again, while all the competitive benchmark products did show a varying degree of chalking. So when taking the performance and stellar EHS profile into consideration, the 8016 is going to be the clear champion in a race between its incumbent competitors. I will now take a step in a newer direction, looking at the silicone-acrylic blends, as we've had, like I said before, significant interest in the hybrid space since the initial launch of 8016. We knew from our initial experiments that 8016 was indeed compatible with many acrylic emulsions and have since been able to prioritize quantifying the space. For our initial silicone-acrylic study, I chose 2 Dow main coat acrylic emulsions that find utility in the industrial direct to metal space already, those being the 5045 and 4950 emulsions. I held the formulation consistent for the data that I'll be sharing over the next couple of slides. The optimized pigment to binder and pigment to silica ratios from the high temperature studies were used for all these formulations. Therefore, for the comparison I'm going to show, I only looked at varying silicone to acrylic ratios so I could best understand and quantify the potential synergy between the 8016 and acrylics. Testing completed included dry and wet crosshatch adhesion after several curing or drying protocols, which encompass the traditional testing schematics for silicone and acrylic paints. These included adhesion after ambient cure or dry at 24 hours and at 7 days. And then your traditional silicone heat cure cycle of 200 C for an hour, and after high temperature exposure at 325 C for approximately 1 week. In addition to the adhesion, color and gloss measurements were also taken in triplicate, pre and post heat exposure. I'll summarize our findings before I share the raw data for adhesion, color, and gloss. Simply put, as you increase the silicone content in either acrylic emulsion, you improve the film integrity, the adhesion, and you decrease pigment removal or improve cohesion post-heat exposure. And all formulations containing 8016 did show an improvement in color and gloss retention. Of course, all of this is expected. As you add more silicone, you have better heat resistance. So I'll share now the level of improvement. For adhesion data, we collected this according to ASTM D3359-17. And to simplify the charts, I left off our heat cured data as all of the heat cured formulations showed excellent adhesion. The tables here show 2 acrylic emulsions in the top row, the left table being main coat 5045 emulsion, and the right table is the data for main coat 4950 emulsion. From there, as you move down, you increase the level of silicone content. So each table shows the same 25, 50, and 75% silicone modified of that respective acrylic before displaying on the bottom row the all silicone formulation or 8016 performance without acrylic. This view gives a really nice illustration, in my opinion, of the obtainable performance spectrum, starting from that pure acrylic formulation, increasing silicone content, and then showing 8016 pure silicone-based formulation at the bottom. The color coding is done via conditional formatting by column. What this means is the 24-hour dry adhesion is compared to other 24-hour dry adhesion results in that column and is not compared to the 24-hour wet results or 7-day results, for example. And the trends observed were consistent between the acrylic binders. It is confirmed here that both acrylics do have excellent adhesion to cold rolled steel after 24 hours and 7-day ambient dry. Where they're going to need a boost in performance is in that post-heat adhesion. This was very low or even non-existent in the case of 4950. And this is where we see that silicone inclusion linearly improved the high temperature resistance. As you add more 8016, you increase the dry and wet post-heat adhesion. Of course, the silicone binder on its own, shown in that last row on either table, does exhibit the best post-heat adhesion. My first hybrid study echoes what I've said now many times throughout this webinar. This set of silicone acrylic performance data enables us to make better recommendations on starting point formulation depending on the individual application requirements. Here, let's start by looking at the table on the right. This is color change data, or delta E, after high temperature exposure. The left column indicates how much silicone and acrylic are in the formulation. The top row is all acrylic, and then the silicone content again gradually increases as you move down the table until you get to that last row, which is pure 8016, similar to what I showed on the last slide. The right 2 columns show delta E for the 2 acrylic emulsions, 5045 and the 4950. And the conditional formatting in this case is again vertical. So we're comparing all the 5045 column to each other and not to the 4950 data, and vice versa. The color change for both acrylics as sole binders is poor, but as you move down the table in either column and increase that silicone loading, you improve the color retention. including, of course, the bottom row or the formulation with silicone binder only, showing those best post-heat color retention results. If we consider gloss retention also, as you increase silicone content again, you're moving down in the table, you boost performance. Comparing the acrylic formulation to the pure silicone formulation, we see a huge jump in gloss retention. We are very familiar with this concept, as organic polymers don't tend to hold gloss well when exposed to high temps. They degrade, they burn off, there's nothing left to hold that initial gloss. Okay, so we know that 8016 can improve post-heat, wet and dry adhesion, and color and gloss retention of waterborne acrylics. But I want to look at the data from a different perspective. Let's say we're formulating with 8016 resin, and while the post-heat adhesion performance is excellent, we know less than optimal ambient dry adhesion, whether that be the 24-hour or 7-day. And this might be required for handleability or moving coated metal parts before it would see a heat for bake cure and application. And here I'm referring to that top row in the left table. The post-heat adhesion is great, but we do have a need to improve that ambient cure adhesion. So we can look at modifying the 8016 versus modifying the acrylic like we examined before, or adding a small amount of acrylic to the silicone formulation to improve its ambient dry properties. So the top row is 8016, followed by 25 and 50% replacement with the 5045 emulsion. And the last two rows are 4950 modification at the same 25 and 50%. And in both cases, when just 25% of that silicone binder was replaced with the acrylic emulsion, the 7-day ambient dry formulation showed much better dry and wet adhesion without surprisingly drastically compromising the post-heat adhesion. So this further allows us to broaden our reachable application space now that we know that spectrum of silicone acrylic performance. Okay, I have reached the end of the data sharing for the webinar, but I do want to quickly wrap up by concluding a few take-home messages. The DOWSIL 8016 waterborne resin addresses a previously unmet market need for a silicone resin that is truly delivered in water-based form without solvent inclusion that can compete with the traditional solvent-based silicone resin performance. In addition to the excellent performance, 8016 eliminates EHS concerns inherent to solvent-based resins and allows for even lower VOC formulating. Unique to the 8016, I talked about its excellent compatibility with organic binders. Today we covered the acrylic space specifically, and new to this venue was the release of this information, which serves as a really good foundation for the wide range of obtainable performances. This is going to enable us to provide data-based formulation recommendations for light, medium, and heavy-duty industrial applications. With the evolution of DOWSIL 8016 and the breadth of knowledge within technical service groups, together Dow and Univar are positioned as preferred partners when it comes to the development of innovative and sustainable solutions. And you can find literature on 8016 at dow.com, and samples are available upon request. With that, I'll finish by thanking you for your attention during this webinar and further extend that in thanking Univar for the organization of this great event.
Well, thank you, Jennifer. That was a great presentation, and we'll go right on to the next segment. And at this time, we are going to go ahead and open it up to questions. And in doing so, just a real quick reminder again, go ahead and submit your question via the chat box feature. Go ahead and click on that question box you're going to see. As the diagram indicates above, you can write your question in that bottom box. Only the presenter will see the question. You'll remain anonymous. So thanks again, and we'll look forward to seeing the questions, and I can see they're starting to come in now. So here they come. We are now beginning to get that first question. Here it comes. And with that, just know, in case we don't get a chance to actually answer all the questions, we'll have an opportunity. Someone would reach back out to finish that up. But the first question, Jennifer, is will the addition of DOWSIL 8016 to a waterborne acrylic emulsion improve the overall UV durability, and do you have any data on this?
Great question, Rob. Yeah, so we know that silicones are great with UV resistance, that silicon-oxygen bond is strong enough to resist degradation with the high UV energy wavelengths. And so usually you would add silicone and therefore improve UV resistance via dilution of an organic polymer. And theoretically, this is what we're expecting with 8016 right now as well. You're going to improve the UV resistance of organic polymers, in this case acrylics, by dilution. We have submitted samples to validate this, and then through those samples we'll determine whether we would need a UV absorber or other additive as well. So I can get back to whoever that was when we get that data back.
Okay, great. Then the next one, which Dow acrylates are compatible with the Dow 8016?
So I tested 5045 and 4950 to start with. They have the same minimum film formation temperature or a similar TG as well. And that's really what we're going to want to take into consideration. I can answer it based on theory, but we have acrylic experts internally that can comment further on the number or density of functional groups on different acrylics to see which ones may be compatible, knowing that the 5045 and 4950 are. So I guess, yeah, you would want to take that TG into consideration and then the functional groups. And what we know right now is that anything similar to that 5045 and 4950 would be compatible, but more than happy to answer specific questions or give a longer list after consulting with the acrylic experts.
Another question did come in that is similar to it, but adds a little bit of an extra twist to it. They're asking the same thing about compatibility with alkyds or SBRs, and are there any formulating tips that might be given to help with that compatibility?
Yeah, so we haven't looked at modifying other organic resins yet. Acrylates were and still are the focus of this initial hybrid endeavor. But of course, as we uncover more unmet needs or unmet performance needs in the industry, we can look into this further. That's how we started with this acrylic modification study, was the overwhelming interest we had in that. So we'll note that that was of interest, but theoretically, it's always going to depend on molecular weight and cross-link density of the organic polymers, just like it would with the silicone. And then if there are compatibility issues, we would, resort to possibly a coalescing solvent or other co-solvent, and then, maybe a lower molecular weight silicone with higher phenyl functionality to compatibilize them may work as well.
You had touched on another question earlier in your presentation around PVC loading or PVC, and maybe you could review that. What's the range of PVC recommended? I think it was slide 17, Jennifer, that you touched on that one.
Yep. So I tested about 50% PVC, but 40 to 60% was looked at initially, and all that was fine. It's going to really depend on the performance requirements, which is why we showed that range of pigment loading to show how performance changes as you increase or decrease the pigment loading from that about 50% PVC that I recommended. And then, interestingly, I will be looking at closer to 15 to 25% PVC, in the near future for the higher gloss films.
How about it? Do you have any experience with coatings on organic substrates such as carbon to carbon?
The short answer is no. But building on that, I expect that formulation tweaks would have to be made, but I don't think it would be an impossible adventure to do that. So we haven't done that though, so I can't comment on what formulation tweaks exactly. I can provide recommendations if there's specific issues once that's tested.
Okay, thank you. Is DOWSIL 8016, is it derived from a bio-based system? Does it fulfill, or would it fall into a sustainable material category?
The 8016 wasn't derived from bio-based system, but it obviously has that improved sustainability profile when you compare it to the incumbent technology that would be necessary for similar performance.
Right. Again, basically eliminating solvent, utilizing. Next question, have you tried a HEUR or HEUR type thickener like RM99.5 in the DOWSIL 8016 formulation?
Again, I hate to give the short answer of no, but that is the short answer. We were given the recommendation of the ASE 60 and pretty much stuck with that the whole time. It didn't show us any performance issues, but of course, again, we could consult that acrylic expert, someone that works with thickeners on a more regular basis, and see if there may be some other products, if there is an issue or concern with adding the ASE 60 from an individual formulation point of view.
The next one, would you have any suggested condensation catalysts that you might be able to comment on?
Yeah, so we have, you can use a hydrolysis or condensation catalyst with this system. We've actually started looking at more on the hydrolysis side. Tizer has a couple of titanates that can be used in this water-based system. Specifically the Tizer TE and the Tizer AA are being explored, and this has shown initial promise at about 1 to 3% on resin solids, which is typical for any catalyzed required system. But those ones are recommended, and then some that will be coming. We've looked at cyclic tertiary amines before, and those had some initial promise, but those two Tizers are going to be the main recommendations. And then King Industries also has some KCAT catalysts that are not titanate based that work well for hydrolysis that I'll be looking at as well, and I can discuss those offline because I haven't gathered any data on those quite yet. But from a theoretical perspective, they would work just as well.
And then adding a second part to that question, could you replace the heat curing with just using a catalyst?
That is the goal, or the golden ticket here. We're working on that. Right now, we do see, longer dry times, obviously. So to achieve the hardness development that you get when heat curing, we were looking at several days, upwards of a week when we catalyzed, which is why we're still trying to dial in on that catalyst package to hopefully drive that hardness development much quicker. But that is the end goal, and depending on handleability requirements, it may be okay right now with the Tizer TE or AA.
Okay, great, thank you. The next one, has the adhesion of this material, the 8016, has it been tested on concrete?
No, we haven't looked at that, but the resin inside the emulsion does have some epoxy functionality, which is what is very pertinent and apparent in most concrete treatment on the silicone side. So again, theoretically, you wouldn't get as high a depth of penetration, but you should get good adhesion.
Yeah. And taking a change of the system, how about the compatibility of the 8016 with a waterborne epoxy system?
Again, yeah, we haven't looked at that. I don't expect any issues, but that's going to have a lot of different facets to look at when dialing in on specific compatibility. So I'd say try it, and if there's an issue, we have some formulation tricks that we could use with the 8016 specifically. And then, of course, future generations, we can take that into consideration as well.
With that being said, on the epoxy side, what's the possibility of it formulating with polyurethane dispersions to improve the adhesion?
Improve adhesion to what substrate is going to be the critical question, but it's kind of the same thought process. It has epoxy functionality. We know that we get good adhesion by itself to OH functional substrates or metal substrates, inorganic substrates. So I don't see any issues detracting from adhesion. And of course, with the alkoxy groups, you'd only further improve that theoretically.
Perfect, good, that makes sense. And then the last question that we've got up today is why an ASE was used in the rheology modifier, and is ASE bad for corrosion?
It's a really good question. I have heard that in the past, but in initial corrosion studies, it did not look, the 8016 system I've shared today looks good. We're still testing that further, and of course, implementing lots of formulation tweaks to see which parameters are really going to give us the best corrosion resistance. But that initial recommendation of the 60 plus seems to fit the good balance of properties around the board. So I'd still stick with that, even in a corrosive prone environment. At the low loading level, of course.
And so that was the last question that we've got up today. And if anyone has additional questions that they might like to have addressed, please feel free to reach out to us, and we will follow up with them or follow up with you to make sure that we have a chance to help you with that. And if you need a sample or you have, again, additional questions, don't hesitate to contact your local Univar account manager or even reach out to our customer service team, or you can reach out to us via the web. But definitely we want to make sure if you've got questions that we're able to take care of those. And quickly, we do have some additional upcoming webinars that we're spotlighting with our series. So the next up will be Kraton, and they'll be utilizing low viscosity HSBC polymers for low VOC coatings. And then King, concept to reality role of acid catalyst. And then Dow is in the next spot again with fundamentals of direct to metal coatings. So again, we'd love to see you as part of these industrial coating spotlight series. And I want to tell everybody, thank you for joining us today. Have a great afternoon. And we really appreciate the time you took today, Jennifer, to do the presentation and all the support from the Dow Silicones group. So thank you very much, and look forward to seeing everyone at the future webinars. Have a good afternoon.